Of the morning. It's Professor Lane Hughston, and Lane has been coming to our series for quite a long time. Maybe he not has met Matthew's standards, but almost close. And he'll talk today for us on the determination of the Levy exponent in asset price models. Lane, thank you so much for coming.
Well, thank you, Max. I've known Bruno, I think, for 25 years or even more, and I remember, and I was reflecting over this with Jim at breakfast, when the news of his famous formula spread through the investment banks like a California wildfire. It was very sort of impressive. And I thought it would be appropriate on the occasion to address a calibration type problem. Not exactly the same as the problem that he originally looked at, but something, at least broadly speaking, in that spirit. And this is about the determination of the Levy exponent in asset pricing models. So this is work with George Búzios at Goldsmiths College. And the details can be found on a paper which is posted at the archive, which you can easily find. So in general terms, we're concerned with the extent to which derivative prices, when they're taken at some initial time 0, can be used to infer the nature of the jump process when we're looking at models where asset prices can jump. And to this end, we'll look at a specific problem, namely we'll consider geometric Levy models for assets and ask to what degree or extent the present values of derivatives can be used to infer the Levy processes driving the models. So in what follows, I'll assume familiarity with Levy processes and their applications. And here there's a broad literature, and I've mentioned in the slide here several well-known references. In what follows, we'll be mainly concerned with one-dimensional processes, although the general ideas can be extended into higher dimensions. For convenience and perhaps for the benefit of students, I'll recall a few definitions and classical results. This will also help to establish the notation. This will be familiar to the experts, but nevertheless, a random process C is a Levy process if it satisfies certain conditions. There's an independent increments property, there's a stationarity property, and then we require two important technical conditions, namely a continuity and probability and the Cadillac property. And when you put all of these together, then we have a Levy process. And then it's a big important result that dates back to Levy and Kinchin that the Fourier transform of a Levy process is given by a rather explicit formula, which involves a pair of constants P and Q, and then a so-called Levy measure nu. And we recall that a Levy measure on the real line is a measure that such that nu of 0 is 0, and then there is a certain integrability condition that has to be satisfied, which is kind of characteristic of the whole subject. And this condition is quite interesting because it's a point of detail that was missed in Definiti's original analysis of processes with independent of increments, and Levy came and sort of triumphed by seeing the light in the matter. Kinchin, on the other hand, eventually produced the formula in the form that we understand it now by purely analytic methods and stands as a sort of cornerstone in the theory. Well, for applications in finance, we need some further conditions, and we'll typically work with Levy processes that admit exponential moments. So this means if we form the expectation of e to the alpha c, then we require this to be finite for some set in which alpha belongs that includes the origin. And if a Levy process satisfies this condition, then we say that it possesses exponential moments. Now the point is that if exponential moments exist, then there exists a kind of real version of the Levy-Kinchin formula, which is the one that we'll work with in practice. And this allows us to define a real Levy exponent psi of alpha, which is given by this expression in formula 5. So again, the constants p, q, and the Levy measure nu appear, but now all of the expressions are manifestly real, and we can work with this analytically. The condition on exponential moments, incidentally, can also be expressed directly in terms of the Levy measure, and that's given by this formula 6. And many authors find it convenient actually to start with that condition as a sort of defining condition for exponential moments. The key point here is that one needs exponential moments in order to progress with the development of financial models. And it's a rather curious matter because when Mandelbrot first started looking at the idea of using Levy processes in finance, he was really interested in infinite dimensional distributions, and he was interested in the case when these distributions had no moments. But this is precisely the case that is excluded with exponential moments. So strictly speaking, in the language of the theory, we're looking at processes that possess thin tails rather than fat tails. And one might have thought that this was perhaps a hindrance on the generality of the model, but on the other hand, it's another classical result that if a Levy process is bounded, even at extremely high levels, like a billion, then that's enough to ensure that exponential moments exist and that the process has thin tails. And I can't imagine a single financial application that would be invalidated with the assumption, let's say, that the asset price was bounded, below, let's say, a trillion. Even hyperinflation wouldn't quite reach that point. So one needs to really rethink some aspects of the issue of the finiteness of the moments. Well, let's come back to the main point. I'll mention one or two well-known examples. There's Brownian motion, for which the Levy exponent takes the form 1/2 alpha squared. And then there's the Poisson process, where the Levy exponent takes the form m times e to the alpha minus 1, where m is the intensity of the process. And then there's a similar, slightly more involved expression for the general compound process involving the moment generating function of the size of the jump in the compound Poisson process. Then one has more elaborate processes. There's the gamma process, which has so-called infinite activity, but there's an explicit expression for the Levy measure in that case that is well known. The use of the gamma process in finance seems to date back, as best as I can tell, to a paper by Hughston, written in the same year with his famous paper on stochastic volatility. This paper of Hughston on the gamma process is less well known, but in some ways is quite interesting. Then there's the VG process, the variance gamma process of Madan and co-authors. And a more general family, the truncated stable family of Levy processes, otherwise known as CGMY, which has been investigated by a number of authors. There are many other examples, too many to mention here, which have been explored in depth in the literature. So we'll be looking at the so-called geometric Levy model, which can be viewed as a natural extension of the geometric Brownian motion model in asset pricing. So we have a one-dimensional Levy process. We assume it exists with exponential moments. And then we have a martingale that we can construct. So this is the Levy analog of the standard geometric Brownian motion martingale that one's familiar with. And you'll notice that the Levy exponent appears in a kind of key position here. You'll see that if psi is equal to 1/2 alpha squared, then this reduces to the familiar expression that one has for geometric Brownian motion. So providing that alpha lies in the set A where exponential moments exist, then we have a nice martingale. So armed with this martingale, then you can begin to build up a class of asset dynamical models. And for a model, basically, you need several ingredients. You need a pricing kernel, a money market account, and one or more risky assets. So first we'll consider the pricing kernel. For those of you who may be unfamiliar with the idea of pricing kernels, there's an extensive literature on this. Duffy's book contains a good account of it, and Hunt and Kennedy and Cochrane's more recent book, State Price Density, Stochastic Discount Factor. These are other words for the same thing. So in the case of a Levy model, what we do is we let lambda be a positive constant, and we require that minus lambda should lie in the set A for values of alpha for which exponential moments exist. We've required that this set is open and that it contain the origin, so we can find values of lambda such that minus lambda is in A. And then we construct the pricing kernel by taking the simple discount factor with constant interest rate times the martingale associated with minus lambda. Then for a non-dividend paying asset, we require that the product of the pricing kernel and the asset price should be a martingale. And the model assumption here is that this martingale also is a canonical Levy martingale. So we'll assume the existence of a parameter beta. So then if we divide each side by pi and rearrange, then we get a formula for the asset price. And this can be rearranged a little bit further, and we get a nice expression for the asset that shows clearly what the excess rate of return is in a Levy model. And I think this is rather interesting because you can see that the expression for the asset price is divided into several parts. There's the initial value, and then there's the usual term involving the interest rate. And then there's the martingale with volatility sigma. And then finally, there's the excess rate of return component. And the point is that the excess rate of return is given by an explicit expression in terms of the Levy exponent. And this involves psi valued at sigma, psi valued at minus lambda, and psi valued at sigma minus lambda. And one can show, although it's not altogether trivial, that for all Levy models, the excess rate of return is positive. For sigma and lambda positive. And furthermore, that it's an excess, it's an increasing function of sigma, and it's also an increasing function of lambda. So if you increase the volatility, then the excess rate of return increases. If you increase the risk aversion parameter lambda, then the excess rate of return increases. These are all properties that one is familiar with in the Brownian model, but the point is that the same ideas carry through in a nonlinear way in the Levy theory. Well, this leads us now onto the main topic, namely the determination of the Levy exponent. So, if h is the power, if h is the payoff of a derivative at time big T, then its initial value h naught is given by the expectation of the product of the pricing kernel and the payoff. The pricing kernel takes into account both the discounting as well as the relevant probability weighting you need for risk adjustment. So what we'll do is we'll consider as an example a one-parameter family of power payoff claims. So this is kind of an option where the payoff is given by a power of the value of the asset at maturity. So then the value of such a derivative is given by the expectation of pi times the asset price raised to the power q. Now for some values of q, for certain Levy processes, this value may be infinite. So we'll assume that the value of the derivative is understood as taking values in the extended real numbers. And then we'll look at h over all values of q. Now, we can proceed to value the derivative explicitly. Just to set the scene, we can consider briefly the case of geometric Brownian motion, which is a familiar one. You may have even done this exercise yourself. So if you take the usual expression for the asset price in geometric Brownian motion at time big T, multiply times the pricing kernel, raise the asset to the power q, and then take the expression, then you're left with an explicit formula for the value of the derivative at time 0 as a function of q. In the Brownian case, this is finite for all values of q. And perhaps the key point to note here, which doesn't come as a surprise, is that lambda drops out of the formula, that the value of the option only depends on sigma as well as the data given by S naught and the interest rate and the maturity date. So we can proceed with a similar calculation in the case of the Levy model. So if we take S and raise it to the power q and multiply it times pi, then we obtain this expression involving the Levy process and the Levy exponent. Taking expectations, well, it turns out once again, just as in the Brownian case, there is an explicit formula that can be obtained. The calculation is straightforward enough, and one can work out the value in terms of the Levy exponent. It's perhaps remarkable that an explicit expression exists, because this isn't always the case with Levy process-related calculations, but it does, and this means that it allows you to study in detail the relationship between a Levy model and the values of derivatives. One thing that follows, by the way, if you look at values of q corresponding to q equals 0 and q equals 1, this allows you to determine the initial value of the asset and the interest rate. So from the values of derivatives, we can work out the implied interest rate in the model and also the initial value of the underlying asset. So this means that if we go back to the formula for h naught of q, we can divide by a term involving the interest rate and the initial value of the asset, since we have that data, and take a logarithm and divide by t. And then this gives us a function which we'll call d naught, which can be thought of as representing the data supplied by the family of derivatives under consideration. So what this means is that we can now proceed to work out the Levy exponent, or at least as best as we can, in terms of the underlying data. And then this leads us to a result. And I'll try to state it in precise terms. So we'll assume that the prices of power derivatives with payoffs given by S raised to the power q are given for all values of q for some non-dividend paying asset with a price process that is known to be a geometric Levy process. And we assume also that the pricing kernel is a geometric Levy process driven by the same Levy process up to some constant factor of proportionality. But we don't necessarily know what this constant is. In other words, we don't a priori know what the risk aversion factor is. Then from the data, one can infer the structure of the Levy exponent completely up to a transformation involving a pair of constants. In other words, if we replace psi by psi of alpha plus mu minus psi of mu plus c times alpha, where c and mu are constants, then this represents the freedom modulo which the Levy exponent is determined. Well, the proof of that is a straightforward algebraic calculation involving the formula that I've given to you. So the point is that, in summary, the Levy exponent is completely determined by the power payoff claims up to a transformation involving a pair of constants. So let me just finish off by making a few interpretive remarks. So what is this freedom that appears here? Well, it can be looked at in several different ways. This is precisely the freedom that one has in a so-called Echar transformation. So we can say that the family of derivative prices, in this case power payoff claims, allows one to determine the Echar family of the Levy exponent for the underlying Levy process driving the model, modulo an irrelevant linear term. So the way to think about the Escher family is that it represents a kind of a noise class. So each different Levy process represents a particular type of noise, but all Levy processes belonging to the same Escher family can be regarded as belonging to the same noise class. So for example, Brownian motion and Brownian motion with drift are a pair of Levy processes that are related by an Echar transformation, and we can say that they belong to the same noise class. And the Poisson process with one intensity and the Poisson process with another intensity constitute a family of Levy processes that are related by Echar transformations. So we can say two different Poisson processes, but with the same, with different intensities, let's say correspond to a pair of Levy processes that belong to the same noise type, and so on. So in this sense, the knowledge of the values of the derivative at time zero allow you to completely determine the type of noise that is driving the model. Another way of putting it is that the prices of derivatives can be used to determine the risk-neutral Levy exponent, the Levy exponent in the risk-neutral measure. This is not surprising, of course, because if you're going to work with options data, then certainly the best you can do is a result that is essentially a calculation in risk-neutral measure. But the point here is that you can get the Levy exponent in the risk-neutral measure, and then from there one has a family of Levy exponents that are related by the measure transformations away from the risk-neutral measure. So if you like, the remaining freedom then corresponds to a family of possible real-world Levy exponents compatible with the given risk-neutral Levy exponent. So as you see, the calibration problem, the theory of the calibration problem can be more or less completely solved in the case of Levy processes. And I think it's rather surprising that given the values of derivatives at some initial time in a Levy model where you're not told anything about the Levy process in advance other than it has exponential moments. It can be finite activity or infinite activity. It can be a discontinuous, like a compound Poisson process, or it can be continuous, like Brownian motion. But from the values of derivatives, you can actually back out what the Levy exponent is, which means that you can say what the nature is of the jumps that are driving the model. Well, I think I'll conclude on that point. Thank you for your attention, and happy birthday to Bruno. Okay. Okay.
So I invite Elaine to join Carol here on the bench, and start questions for both of speakers.
So I have a question for Carol. So the implied correlation that you find is just one example of implied correlation that would work, right? So there's a lot of them which would work and reproduce the option on the index versus the individual components. So would you still be comfortable like pricing an option, let's say for example on technology plus financial using the one that you find?
Yes.
Why? Because there's a lot of others which work.
Okay, so there are many that works, but if you use principle of maximum entropy, it says that like if you choose this one because it exhibits maximum entropy, it's the best you can do given the information you have. And so if you choose another one, you're actually using information that you don't have. So by maximum entropy, you should choose this one and not another one. So that's why also like there's some literature on like finding, so for instance, picking the density, like the risk total density of one asset when you know only strikes, a finite number of strikes, then there are many such distributions because you don't know a continuum of strikes, and you can choose the one that exhibits maximum entropy. If you really don't know anything else, and you don't have a priori, if you have a priori information and you want to add them, then you should actually not pick maximum entropy, but add this information and take the maximum entropy given this additional information. But if it's all the information you have, I think this is the best you can do. So yes, I would take it, and I would be confident to use it.
So I think George has a question.
Yes, just a comment about Carol's response. Yeah, I would be confident with maximum entropy too. I think that given that you don't have extra information, that's the best. But perhaps there are other criteria that you might want to minimize, let's say, variance or something like that. So you might want other ones. But this is, I also am a strong believer of maximum entropy.
But if you have another criteria, then I don't know how to solve. So
Yeah.
the method I have magically end up being maximum entropy, but I don't even know why. But yeah. And if you give me another criteria to choose the risk total density, I don't know how to construct this multivariate distribution that exhibit the criteria you want. So that's actually the only one I can do.
At least one. I actually have a question for Lane. Lane, so you did the computation of the power options, and you can expand sometimes more complicated functions in terms of powers of functions, some kind of generalized Fourier transform. And I wonder if you have tried to perhaps extend that, perhaps for more complicated. Would that be feasible? Would that make sense? Like, you can integrate over the different powers.
Yes, well, let me comment on that. So Georgia was commenting, if I understand correctly, that, well, we have expressions for the values of derivatives based on powers of the terminal value of the asset. And why not consider a Fourier transform and to look at more general types of derivatives? And indeed you can. I mean, in fact, we do that in the paper, which I mentioned. And so you can take things a step further and look at imaginary powers for the payoff of the option. And then a little bit of reflection shows you that this is, in fact, essentially a Fourier transform. And so one can work out, again, the same conclusion, but now using essentially Fourier type payoffs for the option, dividing them into real and imaginary parts, treating them as two separate claims. So explicit formulae can be derived in that case as well. And then, assuming that you're dealing with a payoff that is of a sufficiently nice type, then you can express the value of the claim in terms of an inverse Fourier transform formula. And for the claim itself, I mean, what one requires is that the function be nice in the sort of classical sense of distribution theory. So Lighthill's definition of niceness is we require that all of that the payoff function be smooth, that it have infinite derivatives, and that if you multiply it times any power of x, that it should still have infinite numbers of derivatives and fall off nicely. And providing these conditions are satisfied, then the Fourier transform can be taken, and the inverse Fourier transform will give you exactly the original payoff function back again with no discontinuities. And then this allows you to construct a portfolio of imaginary payoff derivatives to give you the general value of a derivative, providing only that the payoff function satisfies these asymptotic conditions. Now, a call option doesn't satisfy these asymptotic conditions, and any payoff function that's unbounded clearly doesn't either. But in those cases, one can use
Put call parity.
more extended versions of the Fourier theory.
Okay, thanks a lot. Thanks a lot for a nice talk.
There was
So one last question then.
Just a quick one for Carol. Did you try something more, a little bit more sophisticated, a rolling window? Because I understand you look for the average pricing of the option, but you get something very wrong when the market change. For example, XLF, XLK, financial and tech, it was very sensitive to interest rate change. So for example, when Trump get elected, the correlation completely changed overnight. Your model seems, because if you're using just 30 days, you don't think that the world can change, can drift. You tend to have big error when you price your basket option.
Yeah, I'm not sure I understood the question well.
Because you use just 30 days, isn't it, to price. You show that there is a negative correlation premium.
Yeah.
Okay, just using a 30 days.
So
But because the
may use a daily, so on one day I use options that have maturity of 30 days or more, in fact. The smallest available above 30 days. And with enough strikes. So we pick each time, like sometimes 32 days, 35 days. Like it depends what's available on that day. But each day we have a snapshot of all the option prices available.
Yes,
We don't average them, so I don't understand.
the fact that you basically, the change in correlation can be sharp, it can be clustered in some particular days. For example, for this pair, is interest rate sensitivity, especially in the last couple of years. So
Wait, yeah, okay, so you think it's interest rate that causes the...
one of the reasons is interest.
But we do have, but so which interest rate would you take?
US
Like on
10
each day
years.
we update
$0
the treasury bill interest rate. I think we take as interest rate the treasury bill rate for each day. So we update it. So if it,
Okay, I can speak offline. I can show you what I mean. It's fine.
yeah, okay.
Thank you.
So thank you. So I think in interest of the time, we should postpone all the further discussion to the coffee break. So let's thank all the speakers of the morning, please.